Hello. Today we're going to do some examples of the last things that we did. Specifically, we're going to use the transfer function to find the output of systems and also the transfer function to find stability and causality. Let's start with this example. In this example, they give us h of z. They tell us the system is causal. They don't give us the region of convergence. They give us the input and they ask us to find the output of the system. Okay, so let's start with h of z. Again, I'd rather work in positive values of c, so I'll multiply numerator and denominator by z squared, and we get this. Let's factor the denominator into its two poles. Now, once we know what the poles are, there's a pole at z equal to 1/2, there's a pole at z equal to 2, and they tell us that the system is causal. If the system is causal, I know that the region of convergence has to be greater than the largest pole, so I know that the region of convergence is z greater than 2. Now they tell us also that the input is a step function. So I take the z transform of x of n to get x of z. I can do it like this or multiply by z in the numerator and denominator. And I know that the region of convergence is z greater than 1. Now, we need to find the output. So I know that the output of the system in the z transform domain, right, is h times x. So I multiply h times x. And since this is a multiplication, I take the intersection of the regions of convergence. So z greater than 2 and z greater than 1 is just z greater than 2. And so I take this multiplication, this is my region of convergence, and I do a partial fraction expansion on it. Calculate a0, calculate a1, calculate a2. This is all the same things we've done before, so let me put it here on the screen, but you can pause it if you want and go through it. So I get 0, 3, and 2 for the 0, 3, 2, and negative 2 for the coefficients. So this is what y of z would look like once we do the partial fraction expansion. I know that the region of convergence is greater than 2, so it's going to be greater than 1/2, greater than 1/2, and greater than 1. So I can take the inverse of each of these terms. For example, the 3 comes down. The inverse of this term would just be 1/2 to the n mu of n. The 2 comes down. The inverse of this would be 2 to the n mu of n. And the negative 2 would come down, and this would just be mu of n as the inverse z transform. And this would give us the output of the system. Another example, again they give us h of z. In this case has two poles, and again, instead of giving us the region of convergence, they give us that the system is causal. So we know, because it's causal, again, right, it has two poles at 1/2 and -1/4. The magnitude of the largest pole is 1/2, so the region of convergence is going to be z greater than 1/2. And they ask us three things here. What is the region of convergence? Is the system stable? And find x of n so that y of n equals this term here. Now, in a lot of cases, we know the system, they give us the input, and we find the output. This is backwards, right? Here they give us the output that we want, find the input. So for the first part, for the system to be causal, the region of convergence is larger than the largest pole, right? We know that there are two poles, -1/4, 1/2. So the region of convergence is greater than the magnitude of 1/2, right? It's going to be the intersection of these two regions of convergence. In part B, they ask us if the system is stable. Now, in part A, we find the region of convergence. The region of convergence is greater than 1/2, so it includes 1, so we know that the system is stable. Finally, part C, they give us y and we want to find x. And we do this, of course, as we've done all the other things in the z domain. So this is going to be our general equation. In this case, we're going to find x. We can find y, we know h we can do this division to find x. They give us y of n, so we're going to have to take the z transform, which would be this, and it gives us a region of convergence between 1/4 and 2. Of course, it's between 1/4 and 2 because this part, this is mu of n, but this is mu of minus n minus 1, so these terms are the ones that give us the region of convergence less than 2. Now, let's join these two terms together and we'll simplify it to get something like this. So this is our y of z, and this is the region of convergence of y of z. Now, let's solve for x of z. We divide y of z by h of z. We see that there are a lot of terms that cancel, right? The z term cancels out, z plus 1 term cancels out, z plus 1/4 cancels out, and all that's left is z minus 1/2 on top over z minus 2. And so this would be, right, the solution for x of z. Now, we also need to know the region of convergence of x of z. Now, x of z, we see that it only has one pole, and that the pole is at z equals to 2. Now, the region of convergence can include the poles. It's either greater than or less than the poles. So in this case, the region of convergence is going to be magnitude of z greater than 2 or less than 2. Which one is it? Well, we can maybe look at it by inspection, but let's go through it, right? In general, right, the region of convergence of y is the intersection of the region of convergence of h and of x. But this is only true if there are no pole zero cancellations. In this case, if we multiply h times x, since we've already calculated x of z, we see that there's a pole zero cancellation. So z equal to 1/2 is not going to factor into the region of convergence of y of z. Now we know that the region of convergence of y of z is 1/4 and 2. It's greater than 1/4 and less than 2. Because of this, the region of convergence of z has to be less than 2, right? This part of the region of convergence comes from h of z, since we know that h of z has two poles. One of them is at 1/4. And this part here comes from x of z, right? If x of z had a region of convergence that was greater than 2, then the region of convergence of y would be z greater than 2. So we know then that the x of z is this. We know its region of convergence has to be z less than 2. And we can do a partial fraction expansion to be able to invert it and get x of n. So we do our partial fraction expansion like we generally do. We get a 0, get a 1. Once we have those terms, we can inverse each term, right? 1/4, the inverse of course is 1/4 delta n. And this term here, since the region of convergence is less than 2, the inverse of course is going to be minus 2 to the n, mu to the minus n minus 1. And so this would be our x of n for this case. There are some homework problems to do from chapter 6, number 42 to 47. And also, basically, with this difference equation, find the transfer function, find the frequency response. Any questions, as always, let me know. Write an email and I'll try to answer it.